So Stanley studied in École Polytechnique in France, and afterwards he did a PhD in Université Sophia Antipolis with Nicolas Ayash. So we kind of overlapped during our PhDs. So I know Stanley from there. He had the only proper coffee machine in the lab at the time. Now, after that, Stanley actually went to Utah to the postdoc fellowship. And shortly after that, he actually became a research scientist and then a senior research scientist at INRIA. He's located in Paris, in the hospital Pitié-Salpêtrière. And he has quite a bit of contributions marrying geometric objects and statistics, starting with the currents and afterwards now the bigger topic of Riemannian learning. So with that introduction, I will leave it to you, Stanley. Thank you so much for accepting to give us the talk.
Thank you very much, Ender, and thank you very much for the invitation. I'm pleased to be here. I mean, at least virtually, and to see you again. And sure, we'll have coffee and we'll soon. All right, so don't hesitate to ask questions at any time during the presentation. If you have some, I'll try to answer my best. So I don't see you, so just unmute yourself if you want to ask a question. So as Ender mentioned, my interest lies at the crossroad of geometry and statistics. And I think a good example of that is the modeling of the progression of disease. And my main application, my main focus, applicative focus, is on Alzheimer's, Parkinson's, Huntington's disease, so neurodegenerative diseases in a large sense. So let me try first to explain you what I mean by modeling disease progression. I mean, I guess you have a sense of it. But so take the example of the Alzheimer's disease. So Alzheimer's lasts for decades in the life of the individuals, and they involve a lot of different signs or symptoms or brain lesions. So they start very early on by accumulation of neurotoxic protein in the brain that you can see on specific image modality, here a PET image, which after some years end up killing neurons in different areas of the brain. And the more neuronal loss, the more the tissue deforms, and that you can see that on an MRI typically. And once all these processes are advanced enough, then the patients start experiencing different symptoms, a larger range of symptoms of memory loss. In case of Alzheimer's disease, is very known, but also a confusion, spatiotemporal orientation impairments, and different sort of symptoms, which after comes the diagnosis and the phase of the disease that is most known from the general public is the loss of autonomy. Okay, so as you see, it's a progressive disease. It lasts very long, and it involves many different signs that you can see either in the image or I would say in the clinical assessment of the patient. And the thing is that every patient develops the disease a different way. So the main goal of disease modeling, I would say, is try to resynthesize all this process over a very long period of time, and to better understand how this process varies across different individuals. So you see it's like this. It's a statistical problem with kind of a mean and a variance that we want to capture. And with that comes different things that are important, I think, is, so if we know how to well summarize the variability in disease progression, then you will try to predict the progression of a specific individual. And then, especially if you predict the trajectory, what you want to do is to predict the future of the progression. And why do we want to predict the future progression of a patient is basically to determine whether it's beneficial for him or her to be treated at a certain point in time. And I will come back to that. I think it's important today for better designing clinical trials. So maybe you're very familiar with this kind of growth curve, which gives the first idea of what we would like to do is to, which is kind of modeling of the growth of a child here. And I guess you know how to use this curve. So when you have a kid at 9 months, then you report the weight, and it's 10 kilos, and then you see that these measurements fall within a variability range that is typical of these kids at this age. So what we'd like to do is something similar, but we face different challenges. So the first challenge is here, you report the measurements at the different age. But age is not a good marker of disease progression. Okay, it does not make sense to report, for instance, a clinical assessment of a patient at 60 years old, because at 60, some patient might start the disease already, or some might be quite advanced in the disease course. So what we need to do is to realign, if you wish, the measurement according to something which would be more the disease stage, but we don't know, rather than age. So the first challenge, we don't have the x-axis here, which is well established. Oops. Then you read this curve as something which goes from the left to the right with a sense of progression. But actually, this curve is not really constructed like this. What this curve is just at each age, you measure mean and the distribution. But you have no clue how to predict what will happen to these kids after, like, let's say in a year or two. So what we want to do is to build models that could be more predictive of the future, and to fit these points, not just at one age, but to fit this in the trajectory of growth for a person. And the last challenge is that here we have a curve for weight. So you know, there are similar curves for age, and you have similar, but you see each measurement independently. And what we want to do is to do that in a multivariate setting where we can model the joint distribution of the different measurements. And this makes a great sense if you think of very big multivariate measurements, such as an image, for instance, where each voxel, in theory, is an independent, or at least is a different measurement. So having all these challenges in mind, I will just quickly present you in one very simple example how we end up with the idea of modeling disease progression. So that's the key of the method. So you need to just be careful for 5 minutes, and then if you get that, I think you get all the ideas that comes after. So focus on the left-hand side here. So what we have is we say we measure two measurements for one individual. So one measurement is the blue and one measurement is the orange. So let's say it's the weight and age, if you wish, or it's an assessment of your memory capacity and let's say your language capacity or something like this. Okay, so we have one subject here. So we report 4 different the measurement of this individual are 4 different time points, 4 ages, okay, 66, 68, 70, 72 years old. And I report so the 2 measurements at each visit. And the plane curves here represent what we call the model of progression, which is an typical scenario of progression for these 2 measurements in time. And so we need to compare the measurement of the subject with what the model predicts. And we see that here the model does not fit the data of this individual, and this for different reasons. So one reason is that this individual clearly, I mean, he has already started the progression of the disease, if this is disease biomarkers. And clearly, so the onset of the disease is earlier for the patient than it is for the model. So we need to translate the curve on the left-hand side, okay, to account for the fact that the subject has an earlier onset than the typical scenario. What you can see is that the curves grows faster than what we observed in the data of the individual. So we could account for a different pace of progression by changing the slope, if you wish, of these curves to account for the fact that this subject is a slower progressor than the model. And even once we corrected for these 2 effects, what you can still see that the time difference between the blue and the orange curve here is very large for the model compared to what is experienced by the subject. So we need to shrink these 2 curves so that they really fit the data of the subject. And it means that for this subject, the blue biomarkers and the red biomarkers occurs at within a much shorter time interval than what is predicted by the model. Okay, there is a process with 3 different types of operation which can describe the discrepancy between the observation that we see on the data of one individual compared to an average scenario. So the main question is, how do we estimate these plane curves? Because here I assume that we have them. So you can see that now we have like a generative process. And if we have, so the longitudinal data set where we have several patients.
Yeah, I just have a question. Sorry to interrupt.
Sure, no problem.
So the 2 different kinds of markers, the diamond one and the circle one, these are from 2 different patients, right?
Here? No, here is just one patient for which we measure 2 biomarkers, one blue and one red.
And the diamond-shaped markers are from another patient on which the model was trained.
Oh, these ones?
Yes.
No, that's the, you will see that's the corresponding points. If we don't do any types of normalization, then these 2 points should correspond to those points. There's a discrepancy between the ideal points on the curves and these patient's points. Okay, you can just forget about these diamond types of points here. Okay.
Okay. Thanks.
It's not so important. There are the 2 curves, and this is the patient's data, and we fit the curves to the patient's data. I think it will become clear in a few seconds. So now that we have assumed we have, so at the beginning, we just have a longitudinal data set where we have several patients seen at different time points, okay, patient A, B, and C, and for which we have the measurements of the 2 biomarkers. And we estimate the position of the shape in these logistic curves, these plane curves here, so that the average time shift is 0, and the average acceleration factor is 1, and the average intermarker spacing is 0. So in some sense, these 2 plane curves is the progression of the typical subject, the average subject seen in the population. Okay. So I will come back. I mean, formalized idea is an idea of a mixed effect model. So, and the plane curves are the population parameters, and all these parameters, the alpha, tau, and omega, are the individual parameters. And so that's the way we can estimate these plane curves together with the parameters, moving the plane curves to the patient's data. Now, before going into something more formal and with more mathematics, I would just like to do one step further and to show you this representation. So what is on the bottom line is exactly the same thing as in the top line, top row. Okay, so here we have the age in the x-axis and the values of the biomarkers on the y-axis. So in the bottom, we have the first biomarker versus the second biomarker. So here the time becomes implicit in this representation, and all the data fits within this square 0, 1 unit square. So the 2 planes curves here gives now just one single curve, okay, which start at 0, 0 when the 2 biomarkers are the most normal, and end up at 1, 1 when the 2 biomarkers are the most abnormal. Okay. And the 4 different points here represent the 4 different visits of the subjects, and where it's in the x-axis, we report the second biomarker, and the y-axis, the first biomarker. And now you can understand all these 3 different operations on this representation. So what we do with the time shift and acceleration factor is nothing but changing the time parametrization of the curve. Okay, the curve remains the same. We just slide the points on the translate and shrink the points on the same curve. And only the third operation, the intermarker spacing, changes the position of this curve in this unit square by an operation that we call an kind of parallelization, if you wish, of this plane curve. Okay, and this shows you that these 3 types of operation are actually completely generic, because this unit square here is just one specific example of a mathematical space that we can, that is a Riemannian manifold. And this curve here, given by the two logistic, is a geodesic on this Riemannian manifold. The two operation is a time reparametrization of the geodesic. So it can be defined for any types of Riemannian manifold and any type of metric on this manifold. And this operation here, it's an Exp-parallelization. It's a generalization of the concept of parallelism in a Riemannian manifold. And that again can be applied for any types of Riemannian manifolds. So what I presented here is a very specific example of a model which can be applied in many different settings. And just to give you a hint of that, so here it's another types of Riemannian manifold, which is completely different, much higher dimension, where the central line is a geodesic showing the atrophy, the deformation of the hippocampus over time. Yeah, that's exactly the equivalent of this is a geodesic on a certain Riemannian manifold, which describe the deformation of the tissue over time. And what you see on every line, every row, sorry, is a kind of a parallel to this central geodesic, and which describe how the hippocampus changes in time, but with a different geometry. You see a column, you see an hippocampus with different shapes, because at some age or some stage of progression, some have a bigger or smaller hippocampus, some have different, more or less curved or different shape at even for same disease stage. And then you see on the x-axis what is due to time, and the y-axis what is due to, I would say, the natural inter-individual variability. All right, so I come back to this much simpler representation where we have this manifold on the top. So what we do at the end is estimating this central curve here, which is a geodesic, and all this translation, which depicts how this, the distribution of trajectory that has been learned from a longitudinal data set. And you can see that the first and second subjects here with 4 different points are very likely, because they are, the second is nearly very located in the central line. The one is not very far from it. And so these subjects, for instance, have very small, very high likelihood to belong to this, to belong to the population that we have observed. Whereas the third and fourth subject are very unlikely. So the third is clearly unlikely because they have already atypical values of the biomarkers. And the 4 is also atypical. The values by themselves are not so different, but you see that the blue points grows much faster, while the orange biomarkers stay very steady. And that is quite unlikely to be observed given the shape of the model that we have estimated. So just to give you a sense of what we did here is to really learn a distribution of trajectory. And it allows us to position the different subjects on this distribution of trajectory and compute the likelihood of a series of biomarkers.
Sorry, can I ask a clarifying question?
Sure.
So you decide whether it is likely or unlikely based on the translation and rotation and Exp-parallelization that you have to apply in order to fit the function. Is it correct?
Yeah, so that's a modeling choice to limit ourselves to the 3 types of operation. Yes.
Okay, yeah, thanks a lot.
You can imagine to do something more complex, to add more degrees of freedom, but to be honest, I have never seen an application that need really to do that. So, for instance, in this Exp-parallelization, what it does is only to translate each curve, but you cannot change, for instance, the slope of the blue curves while maintaining constant the slope of the orange curve. That would make this curve not parallel, but with a drift, if you wish. And that's an effect we could add, but that we have not done. Okay, is there other questions?
Will you say more about the Exp-parallelization later?
Yeah.
Yeah, okay, great.
So actually right now. So no, I will try to formalize this with a bit of math. So what we built is a hierarchical model. So we assume that there is an average trajectory, which is a geodesic on a Riemannian manifold. And here I assume that the choice of a Riemannian manifold is given by the user or by some modeling choices. Then we derived an individual trajectory with a spatiotemporal transformation of this trajectory that will imply the 3 parameters I have explained before. And we see the observation, the data, as some samples, noisy samples along this trajectory. Okay, so this forms a typical generative statistical model, which also called a mixed effect model. So what is the Exp-parallelization in a manifold? So if we have a geodesic on a manifold, which is so characterized by 1 point and 1 velocity at 1 time point, then to parallelize this curve, we choose one vector in the tangent plane of this point, and then we find the exponential map in that direction to give this point on the manifold, and then we parallel transport this vector along the geodesic, and to find another point here. And if we do that continuously, we build another curve on the manifold, which is what we call the next parallelization of the geodesic on this manifold. So this curve is no more a geodesic; it's another curve, and if the manifold is a Euclidean, it corresponds to the usual concept of parallelism. And the sphere, so in the sphere, for instance, the geodesic is a great circle, so in blue here. And if we parallelize this curve in the direction of the magenta arrow, then it gives this red curve, which is actually what we call a parallel on the surface of the Earth, whereas the geodesic are the meridian on the surface of the Earth. So does it answer the question about the Exp-parallelization, or do you need further clarification?
I think it answers it.
Okay, thanks.
Thank you.
Yeah, I just have a few clarifications to ask.
Yep.
So essentially what you're doing is you're going from an explicit time dependent space to a state space, where time is basically how you move through the state space. It's essentially trajectories, and the more representative the trajectory is of something that actually demonstrates a disease progression, the more the likelihood will be over the distribution in the state space, right?
Yes. So what we will learn is the direction of this main geodesic, which will capture the effect which is due to the progression of the disease, due to time. And in the orthogonal direction will be the other differences that are not due to the progression, but due to inter-individual differences. Yeah, is it okay?
Yeah, and if you don't follow the geodesic, that essentially means you're an out of distribution sample, right?
Yeah, if you are out of distribution, it's either because you are very far from the geodesic, so your measurements are very unlikely, or because the direction that you follow in time is not kind of parallel to this geodesic, so it's very unlikely to be.
Okay.
That's what I mean by this previous example here. So here the 3 is quite unlikely just because it's out of space in some sense. And the 4, if you just look at the cross-sectional data, so all the data are quite likely to belong to this population. But the direction where they evolve is not parallel to this to the direction that we have learned. It's unlikely in that respect. Okay, so to sum up, the population parameters, it's a point, a velocity, and a time, which define a central geodesic. And we have direction on this manifold to parallelize the curve in the different places to fit the data of the individuals. And we add to that the time reparametrization of the curve. And we choose here an affine form of time parameterization function. So at the end, the chase observation of the eth subject is just a spatiotemporal transformation of the subject at time TIG plus noise. Okay, I'll skip that. So the fixed effect is a point, a time, and a velocity, and the random effects. So we have one acceleration factor, which is the slope in this time parameterization function that we assume to follow a log normal distribution. And there is a time shift, which is supposed to be normal distributed, which is the intercept, if you wish, of the time parameterization function, plus this what we call the space shift, which translates the curve and the manifold. And here we assume that they derive, we need a kind of a dimension reduction for very high dimensional manifolds. So we assume that this space shift is a linear combination of a small number of sources in the orthogonal space of the velocity.
Stanley, maybe a clarification question. This might be very simple. I think you know my geometry knowledge better than anyone. So by using the exponential maps, do you actually assume a stationary vector field?
No, not necessarily.
So then the vector fields can actually depend on time and they can change.
Yes, the thing is that I know why you're asking the question. Actually, it's more the time varying vector field which fits more into this framework, because I mean, if you see the velocity here at v0, if you follow this, I mean, like on the sphere, it's not the same v, so it changes in time. So the v normally is time varying, and if you have a stationary velocity field, it's more a Lie group than a Riemannian manifold.
Okay.
In any way, this comes away from the ideas of because what you have in mind is the Riemannian manifold, which is very specific for this deformation space. But if you look at this first example I've shown with just the two logistics, there is no velocity field. It's just a velocity on a unit square. So there is no field in some sense. You see?
I don't actually, because at each point there is a velocity, right? Like even in that example, at each point there is a velocity defined on that manifold, on that 0, 1 square, isn't it?
No. On each point you can define one velocity, the one you wish in the tangent space, and find a geodesic that goes in that direction.
So okay. So at each point there is a velocity, but it's completely free.
Yeah, completely free.
Yeah, perfect.
So sorry, yeah. So in the case of Euclidean manifold, for example, this would basically mean learning a parameterized form of the vector field, right?
No, in the Euclidean space, what we have is a kind of linear mixed effect model. The vanilla mixed effect model, linear mixed effect model you find in biostatistics, where you fit a straight line to the measurement of all the subjects, and you have a random effect on the slope and intercept. So it's not exactly slope and intercept, because I at some point, no, I don't have a. Okay, so yeah, you are image people, that's why. actually, in deformation space, this VZO, for instance, here that I describe here with just one vector, that this would be an entire velocity field in the deformation framework. But here, in most cases, in Riemann manifold, it's just in one velocity, one vector. I will come back to that. Okay, towards the end, I will save time to maybe to show you it a bit differently. Okay, I might skip that unless if you have some questions. So the question is, so here we have a structure of a hierarchical model. So we have fixed effect, which is just a point, a time, and a velocity on the manifold. So here, if the manifold is dimension 2, the velocity is dimension 2, and point is dimension 2, and the time is just one dimension. So in dimension 2, the unit square, this is 5 parameters only. Okay. And alpha is one-dimensional, tau is one-dimensional always. This is 2 scalar. And Vi here is, so it's in the orthogonal space of V0. So if we're in dimension 2, there is only one dimension for Vi. Okay. So dimension 1 also in dimension 2, or it's of dimension d minus 1 in a manifold of dimension d. So the problem is how to estimate, of course, these parameters, which is clearly not an easy task. So as I said, we'll skip this inference unless you have questions. So what we do is basically to build an EM algorithm to estimate the parameters of the model. And it's a bit more complex than that. It involves stochastic approximation and within a stochastic approximation, a step of MCMC. If you have questions, I will be happy to answer, but given your questions, I prefer to skip that and save time for what comes next. So just again, an example of a kind of a vanilla manifold that I showed before. It's just an hypersquare, so unit square in dimension 2, or a cube in dimension 3, or also an entire dimension, where we assume that each biomarker follows a logistic trajectory, logistic progression. It's a very simple types of manifold, okay? Much simpler to what you see in image analysis. And just to give you some more realistic example, so here in a study of Huntington disease, where we have a longitudinal data set of nearly some subjects, I cannot sum up here. And for each of these subjects, we measure 15 different biomarkers. So here we are in dimension 15 with different clinical biomarkers, cognitive biomarkers, and imaging biomarkers. Here, by imaging, I just mean we extracted from the MRI the volume in some specific brain regions, so striatum, globus pallidus, putamen, ventricule caudate, plus more global measurements in white matter, gray matter, and total brain volume. So it's just 8 measurements, and that's it. It's not the whole image. I will come back to that later. And what we have at the end is, so we have this common timeline here that we have estimated, and in this space of dimension 15, I estimated a geodesic. And what I show here, it's each coordinate of this geodesic. So there are 15 different coordinates, and all the coordinates is a logistic curve. And so we see the progression of the different biomarkers over time. And you see that some start very normal, some are already a bit abnormal, even very early on, and they all progress over time. And all biomarkers were normalized so that 0 is the most normal value, and 1 is the most maximum pathological change.
So how did you normalize the volumes of structures?
So there are different ways to do that. We can do the percentile of the distribution of the control distribution, for instance, or do some things a bit more clever than that. But that's the idea.
So from the patient list you have.
Yes, and from and usually the controls distribution.
And Stanley, why are you normalizing them? Why wouldn't you use just raw volumes?
I can use raw volumes, except that if I use raw volumes, I could only use, I would easily use a linear progression curve instead of logistic. If I have logistic, the 0 and 1 are embedded into the modeling choice. Okay, so so the geodesics start at 0 and end up at 1. So I need to account.
Right. So 0 is normal, but it wouldn't be a regular normal volume for, I don't know, Hippocampus, for example. Yeah.
Yeah, and it's also a way we could compare also the different measurements together. Otherwise, I mean, they're all different units, then it's become difficult to compare the position of the curves.
Okay.
But still, this raises the question of, okay, 0.4 here for the hippocampus does not mean necessarily the same thing for cognitive assessment. So again, on top of that, we estimate some threshold that best separate controls from distribution of controls from a distribution of patients. And we report this threshold here, that is kind of pathological threshold, if you wish. And we determine the typical age at which the typical patient crosses this threshold. And this gives rise to this box plot, which shows that, well, here in that circumstances, the biomarker 1 becomes atypical earlier than the biomarker 2. And so from this big spaghetti of logistic curve, what we have derived at the end is a sequence of symptoms and alteration that we can see, starting with the total motor score, which is one of the earliest signs of Huntington disease, plus all the volumes here of the deep brain structures becoming abnormal, followed by more the cognitive and assessments becoming atypical. Okay, and so this describes the main geodesic. So this is the central curve, okay, the curve, the progression of the typical patient. But as you understood, we also have parameters which now position the progression of each subject with respect to this central curve. And so, for instance, we have time shift, which says, okay, the time shift is okay, time shift account for the fact that one subject might be an earlier progressor or later progressor than the average patient. And the acceleration factor says that some are slower progressor and others are faster progressor. And so 1 point here represents one subject and represent the time shift of the subject and the acceleration factor of the subject. And we plot different colors. So in red, it was an initial cohort. It's called track HD cohort. So it's a first cohort that was built. And the interesting thing is that they keep following some of these subjects in another study, a follow-up study, which is track on. And so in blue, you have the subject in the first study that has been followed up during the second study. And in green, you have the new subject that were added. And not very surprisingly, what you can see is that the people that were not included, not in the second study, were the fastest progressor. And that's most likely because at the point in time they started the second study, these probably didn't meet the inclusion criteria anymore. And at the opposite, the latest converters were the ones that were followed up in the second study. So just to give you a very simple example of what we can, how the different subject parameters allows you to describe different profiles of progression across the different subjects. So on the left, what you have is the parameter which describe the whole trajectory. On the right-hand side is what you call the Huntingtonian edge at baseline. Okay, so you have the baseline visit, and as you've seen, so we reparameterize the age of the subject. We map the actual age of the subject to what we call the Huntingtonian edge, which is a time index on this central geodesic. And what you see is that at baseline, at time where people were included, so this red subject were also in the latest disease stage compared to the blue one. Okay, because you can be a fast late converters, but it depends when you are included. You can be a late converter, but if you are included very late, then or can be included earlier in the disease course. So there is a difference between the global characterization of the trajectory and the time at which you are included into this trajectory. All right. So do you have questions on this part before I move to the imaging part?
So I have one question on the previous slide, actually.
Yeah.
So what is the value of modeling the geodesic rather than the individual markers? Would this plot have been different?
Would this plot have been different if
you were to do a univariate analysis of all these markers?
If I do a univariate analysis, then I have no common time axis on the.
Yes, but I mean, you would be able to use. I mean, if you use the age, for instance.
Yeah, but then you mix up because, as I said, you will compare or average the TMS score at 40 years old. But 40 years old for some individual means quite advanced disease stage, so higher TMS than others that will just start the disease at 50. So you mix up age with disease progression.
I see. So that actually allows you to give this common age.
Exactly.
Very good.
Exactly. All the point of the modeling is there, actually. Yeah.
Actually, as a follow-up question, it means that you estimate a global set of parameters for all the biomarkers, right? The translation and the scaling and so on.
Yes.
Yeah. Okay. Thank you.
All right. So as you can imagine, what we can do with Huntington, we can do with any neurodegenerative diseases. So I have plenty of examples, but it's not the point here. I will briefly discuss this also because, okay, the goal I mentioned at the beginning is to be able to predict the future. So here it's another simple example. So instead of the 15 curve, I just have here 4 curves. Okay, it's just for the sake of simplicity. So imagine I have trained the model on a longitudinal data set where I have multiple subjects seen at multiple time points. So here is the main logistics. So this geodesic in dimension 4, and I trained the model. So I know the distribution of all these parameters. Now there is a new patient coming in, okay, that has not been seen before. And I measure the 4 different biomarkers for this subject. And then I can report these 4 different measurements. And what, it was very quick, sorry, but we can estimate the most likely parameters that allows to fit the curve to the point, the data point of the subject. Okay. And given that, now it's very easy, and I just need to read. And this patient is 77 years old, and I can guess what the biomarker of the patient would be at, let's say, 80 years old. And I can use that prediction to make a clinical decision. And the clinical decision we are thinking about is whether it's interesting for this patient to be treated for a given drug at that time, or whether it's too late or too early to treat this patient. Okay, so again, very short, we are very proud because we have evaluated the accuracy of the prediction in the framework of the Tadpole challenge that was run in 2018. And we see that the 3 different models that we have trained on the left give all better mean absolute error than the best method in the challenge. And that was to predict the progression of the ADAS-Cog 13 in people with mild cognitive impairment. Okay, and surprisingly enough, this generalized much better to independent cohorts than the most standard biostatistical methods. I can come back to that later. And that is, I think, so I will just put 1 minute on this because I think it's also important. We think that this allows us to do much more powered clinical trial. So currently, when you do a clinical trial in AD, for instance, you target a certain disease stage, which is defined very coarsely as with a very wide age range, and a clinical dementia rating between 0.5 and 1, and clinical dementia rating is quite a very coarse estimation of the level of dementia of the person. Okay, that's the best we could do today to define what is an early stage Alzheimer's disease patient. And what we propose to do is to use the baseline measurement of this patient and to predict how they will progress in time. And to include in the trial only the patient for which we predict that the outcome measure will significantly progress during the trial. The main idea is that in this population, okay, which is quite heterogeneous, some people will not progress over time in the next 2 years and will stay very steady, while others will progress and during the trial. And if you want to see the effect of a drug, then you need to only prescribe the drug to this person that will progress. Because if the disease does not progress, you can give the drug or not. It's the same thing, okay? Because anyway, since the disease does not progress, the drug does not change the progression. Okay, so there is a strong interest in targeting patient for whom the endpoint will progress during the trial. And so we can see that, so that's a usual type of plot where the x-axis is the treatment effect size. So 0.30 means that here we have a drug that in theory could reduce by 30% the rate of change of the MMSE. Okay, so it's a simulation framework, so it's a hypothetical treatment effect for a hypothetical drug. And for that, you see that with the current selection methods, you need something like 1,200 subjects to see this effect. Okay, so it's just a sample size calculation. And if we limit ourselves to the patient for which we predict the MMSE to change, for instance, between 1 and 2 points per year in the next 2 years, and then you can nearly decrease by 2 the number of subjects to recruit for the same effect size. So I think it gives it explains why it could be interesting to predict how the patient will progress. Because the usual question that you might have is, well, since there is no treatment, there is no interest in predicting the future progression of an Alzheimer's disease patient. And I disagree with that statement, because here I clearly show that at least for clinical trial design, predicting the future is important. All right, so time pass. Do you have questions on that part?
Maybe I can ask one more question there. So in these cases, is there an underlying, so I guess an underlying assumption of the model that is that the diseases progresses continuously. And how well does it hold for the disease that you look at? For example, if I were to do a similar modeling for, let's say, multiple sclerosis, their disease kind of progresses in quantiles, right? So it basically, I mean, you have one onset of, you have one attack, and then you basically jump to another level and so on. But I don't know enough about Alzheimer's or Huntington's, whether to say they're also continuous or they jump with discrete steps.
Okay, the underlying assumption is a monotonous progression. Okay, it's not steady because you have this type of logistic curves that can describe a steady evolution followed by an acceleration at some point. And we can adjust for the time at which this acceleration occurs. So this is not a question of continuous versus stepwise. It's the assumption is the fact that it's monotonous. And that's true for Alzheimer's, true for Parkinson's, true for Huntington. And it's not true, as you said, for multiple sclerosis, where you have this remit time. So some symptoms worsen and then get better, and then worsen, get better, and then you end up in a progressive phase. And that's true that this modeling does not adapt for this type of behavior, with like a zigzag behavior the measurements. And we are working on some extension of that to account for this non-monotonous behavior of the measurements.
Thank you.
Okay. So for the imaging people, I will try to bridge the gap with what I've just presented and what you may be more used to it. So just a glimpse on the LDDMM, if you wish. So, and this I hope will address the question I had at the beginning of the talk. So we assume here, so now this is the 2D or the 3D space in which we'll embed an image or a shape or a mesh, okay? We have control points. So let's say it's in 2D, we have a planar image for the sake of simplicity. So if you have n control points in the dimension D, so all these control points means one point here in a space of dimension n times D. So this define a high dimensional manifold. Then I can define a cometric on this space given by a kernel, and this kernel, I mean, if you think of a Gaussian kernel, it's a function that decays according to the distance between the 2 points. And so this models typically the interaction forces between 2 points, and the closer the points, the stronger is the interaction between the 2 points. Okay. So this defines a manifold and a metric on the manifold. So what I can do is to set up a velocity here. So the velocity here on this, the high dimensional manifolds, it means one 2D vector on each of the control points. And given the initial position, initial velocity, then we can solve the geodesic equation and to find the geodesic, which is the motion of this set of control points in space. And you see that the vectors attached to the points, which is the velocity at the later time points, so it changes over time. So it's not it's a moving velocity field. And given this discrete set of control points, we can use the kernel to define the continuous V, which is in the RKHS defined by the kernel. Okay? So this V is a continuous, time-varying velocity field, which is depicted here in blue. Okay? So it's just the superimposition of the vectors that we have seen on the control points, interpolated all over the place. And now we can integrate this time-varying velocity field to find a flow of diffeomorphism that at the end we can apply to an image or a shape to find deformation of the shape. What you see here, that's the shape, the three different meshes, orange, blue, and green. And what you see is the arrows here is what is on the left-hand side here, that the control points and the vectors attached to the control points, which defines the initial, the geodesic in this Riemannian manifold of dimension n times d. And at the end, what you see is the application of the diffeomorphism to the shape that deforms the shape. And that so the motion of the meshes here is what I depicted schematically by this line on the right-hand side. And that, of course, can be applied to images in the same way, and define a flow of diffeomorphism that you can apply to the image and deform the underlying image. And so now we can define this Exp-parallelization. Exactly, I mean, it's an abstract concept, so it can be applied in this particular setting. So we could define a direction WI here, which is in this n times d manifold. I can compute the geodesic on this to find this point here and to define this Exp-parallel curve. And I can cascade all that. So this defines a velocity field plus diffeomorphism, and then I can see how the shape here is moving, is deforming along an Exp-parallel curve compared to the central geodesic. And if you write this, so I will skip the math, is, I mean, it's just exactly the same as before. It's just you have a complex nonlinear function of the latent variables and the parameters. This only thing that changes is this nonlinear function is here compared to the most simple example I have before. But I mean, if you write it, it's just a mixed effect model with a nonlinear relationship between the latent variables and the observations. And that can be solved nearly exactly the same thing. So there are a bit more subtleties here that I will skip. And so that's, yeah.
Could you go back, please?
Yeah.
So here you have a function that evolves over time as a function of t, but then you also showed this vector field that was evolving in time. And can you please tell what are the, I mean, I guess these are not the same.
No, they are.
They are. So is the motion along the x-axis and the motion that we, I mean, when you had this plot with the vectors that were moving,
yep.
It's the same?
Yes.
Aha, okay.
Yeah, it's time, so it's really the time in the sense of the common sense of time. So it's time, it's the age you wish, or the progression index. It's really time.
So you could say that these structures are evolving in time. It's just that the rates of them evolving from time to time are different, but they evolve in the same way. And that's how you can you learn the manifold as well as the rate dependent, I mean time dependent velocity.
I'm not sure to understand. Yes, I mean, we estimate the time varying velocity field where the time defining this central geodesic here is really the time in the sense of the age, if you wish. It's true that if you integrate, you need to integrate a geodesic here, for instance, to go from that point to here. And here you have another concept of time. For another time varying vector field. The time here is just between 0 and 1. It's a unit, it's an exponential of this. So it's we integrate a unit time, and that time here is no more related to a real time. It's an integration parameter. So maybe the confusion comes from here, but we use this time here really as a real time when we go along the geodesic. So it's true that, for instance, in image registration, for instance, you never, I mean, you consider this time also as an integration time, and you only look at what happens at 0 and time 1, and you find the moving image, and time in between for registration of subject A to subject B. Of course, it's just a computational tool. The time doesn't mean anything. But here, we use this time as to describe how the shape is moving while the subject ages.
I think for me it makes sense. Thanks.
Okay.
Yeah. I don't know.
And so that the last picture I really would like to comment here. So on the top is a geodesic. I mean, some snapshot along the geodesic. So we define what is given is the silhouette here in black. Okay, we did ourselves. And we define the blue arrows here. So that's what is given by the user. Then what we do is we integrate this geodesic. And so the effect of this blue arrow is to raise the left hand of this guy. Okay. And so this is a very simple diffeomorphism of the shape over time. Okay. That when you read it from left to right, it's all driven by the blue. Now, as a user, I will give another set of parameters, which is this red arrows. Okay, and the red arrows allows me to map this silhouette in black on the top to this silhouette on the bottom. Okay, so here I don't represent time. Here, here there is an integration from coming to the top to the left, but this is hidden, and I don't care about this integration time. It's just coming from the top to the bottom. And and it's just the same guy, but just in a different geometry. So you check his hands and move the hands around. And now what we compute from that is the other red arrows, which is the parallel transport of the red parallel to the blue. Okay, so it just changes so for instance, this red arrows follows the blue one, and the other one are not really affected by this blue because they're further away. And for each snapshot here, I can compute how I change the shape on the top to the shape of the bottom. Okay, so I move from the left to the right, and for each snapshot, and go from the top to the bottom, following the blue from going from left to right, and the red from going from top to bottom. And at the end of the day, what we have is at the bottom, we have a movie of a silhouette, which also raises the left arm. So what this operation does is just to translate the motion of I left the left arm, I leave the left arm from one geometry to another geometry. Okay? So this is the Exp-parallelization. It's just, and then I can use, if you give me another silhouette with a different shape, and I can translate the motion of, okay, raising the left arm from one silhouette to another one. Okay, and now if I have a longitudinal data set where I have multiple snapshots of different silhouettes, it has different shapes, then the algorithm at the end, what it does, it from all the red silhouettes that is given as input, it gives a standardized motion of the silhouette, so leaving the left arm from the left to the right in a average silhouette shape. And then you can propagate this back to all the subjects to reconstruct the subject-specific trajectory that goes as closely as possible to the observations.
I know time is running, but I have another question here.
Yeah.
So you mentioned that this trajectory that actually evolves or gets parallelized to the other ones is a geodesic. And at the beginning of your talk, you mentioned that when it is Exp-parallelization, you end up with a non-geodesic.
No, it's not a geodesic. So I said that, I'm sorry, it's a mistake. No, it's the Exp-parallelization curve is not a geodesic.
Yeah, you said that. You didn't say something else. So does that mean that, so when you're building in the original model, when you're building these mean trajectories, does that mean the mean trajectory is assumed to be or modeled to be a geodesic while each patient trajectory are not?
Yes.
And how can we get an intuition about that distinction? Or is there an intuition about that distinction, or is it just an arbitrary mathematical difficulty there?
I think there is no reason for a subject to follow a geodesic. Because the manifold is chosen arbitrary, I would say, and there is no reason for this to be. The reason why we end up with this concept of Exp-parallelization is because if you do the work of Tom Fletcher, for instance, there is a different way where they ensure that every subject follows a geodesic, and then they try to build a mixed effect on top of that. But the problem in that construction is that you need to specify the particular point on the common geodesic. Here, I mean, if I go over here, you know, here, all these parallel curves here, how to say that differently? Okay, in this construction, what is nice, and the property that we ensure. So you have this time shift here. It's defined on point P0, but parallel transport here is an isometry. So if you assume a normal distribution of the VI here at this point, at a later time point, it's also a Gaussian distribution. So here it's a really, so this VI is not, I mean, it's attached to a point because we need that for computation, but intrinsically what it shows is that the whole trajectory is moving. Okay, and that's also a reason why we could smoothly integrate time reparametrization function. Otherwise, you will compare a velocity at different points on this trajectory, and that makes everything up. So that's why I found this concept of parallelism interesting, because it somehow make it intrinsic in some sense. In the sense it does not depend too much on the way this geodesic is parameterized. And that's why we can reparameterize that in time without any problems. Okay, so that time is running, so I nearly finished. I have 2 slides. So one is this one, so I have already shown, but now I think you understand what it means. To have this central geodesic, which has been learned from a longitudinal dataset, and all these Exp-parallel curves, which describe the atrophy of the hippocampus in a different geometry, exactly as for the silhouettes. And okay, the nice thing is that you can combine all that. So to give a complete picture of how the Alzheimer's disease progresses in time, where you have different measurements. So here it's cortical thickness, glucose metabolism in the brain, deformation of the hippocampus, all that synchronized with the progressive onset of the disease. And we can synthesize then the progression over nearly 30 years of age. And plus you have all these parameters that can account for different timing and ordering of all these different radiological and clinical signs when you change the subjects. And you can play it for yourself. There's this web app that you can find. I thank you for your attention, and I put here, so if you want to trade for yourself, so LeSpy is a software package we released for that. So it's also Deformetrica for more imaging and shape-related works. And here's sort of some publication, but I thought you already read some of them in the preparation of this meeting. So thank you very much, and you have some questions. We have still a bit of time to answer them.
Thank you so much, Stanley. So any other questions? I feel like we asked quite a few already during the talk.
Great. I'm sorry I was a bit long, so maybe people have to run another meeting. So anything like this, that's fine.
No, I think this was perfect.
You can reach me out by email if you need to ask a question at a later time point. That's not an issue.
Thank you so much, Stanley.
You're welcome. Thank you very much for your invitation, and have a good afternoon.
You too. Bye-bye.
Bye-bye.
Thanks, Stanley.
Thank you, Bill.